recording now. Thank you.
Let me just say hi to many people I've seen in the chat who it's great to see, and thank you for joining this session.
Yeah. I saw it's great to see everybody virtually. I saw some of my favorite locations in the world: Sedona, Arizona, Wales, all over the world. Fantastic to be talking to you guys today. So let's just jump right into the slides. So we got some slides. We're going to make this very visual. Hopefully a lot of fun for everybody. And Max and I are going to share a journey that we've been on. So we're calling this our amazing astrophotography journey. And the focus of our discussion is actually going to be in this image. So we'll get to that in a second. But let's just start out by saying a little bit about who we are. So I'll go into Max and I's backgrounds very briefly, talk very briefly about the visible universe as a project. That's what we're calling it. And then 90% of our time today, I want to discuss this last question. So how do you take a picture of the whole sky? It brings some interesting challenges, and we'll talk through exactly what we went through to overcome each of those challenges with you. So I'm Charlie Bracken. I'm here in Pennsylvania in the US. It's pretty cloudy here, but I managed, maybe 3-4 nights on a good month of clear skies. And I get out there and have been practicing astrophotography for something like 12 years or so. I've got 4 published books and multiple editions, most popular one being the Deep Sky Imaging Primer, which is basically to take you from beginner to intermediate or expert in astrophotography, hopefully in one book. Max, I'll let you say a little bit about yourself there.
Thanks, Charlie. Well, my background originally was in broadcasting. I worked for the BBC Science Department for 10 years or so. And then I got interested in startups and left the BBC to set up a startup in the early days of interactive publishing. And we were working with an obscure Californian company called Apple at the time, which wasn't anything like the Apple we know today, but that was interesting. I do still, I'm involved in an app publishing company. And as you'll hear later on, one of the things that we're going to be doing with the visible universe is producing an app version of it. But as Christian rightly said, I'm a latecomer to astrophotography and astronomy. I got seriously interested 4 years ago when I attended the masterclass that Christian ran, and it was an absolutely brilliant week. If any of you are thinking of going on one of the masterclasses at Siding Springs, it's just fantastic. And that got me started. And pretty soon I read Charlie's book, which also helped me get up the learning curve. And we met and we cooked up this project that Charlie will tell you more about.
Yeah, it's been quite a journey. So yes, I saw in the question and answer session. Yes, there is actually a discount. We'll tell you about that toward the end of the time today. Okay, so that's who we are. This Visible Universe project, as we mentioned, so it's pretty bold. Our goal here: we want to create tools that guide astrophotographers around the world on what to shoot, when to shoot it, and kind of what good looks like for the best astrophotography objects that are out there. So you've got 15,000 objects in the NGC and IC combined. You've got all these other things to look at. How do you choose which things to take pictures of? What should it look like? What filters should you use? Things like that. We want to give guidance on all of that. And the book is the first step in that. And this was a big project, right? So this is what the book looks like, and just a representative page. And we'll show a little bit more what the book looks like, but this is a full color, hardback, high quality photo book. The book covers 110 of the best objects. That was our homage to Messier's catalog, at least the modern version of Messier's catalog. 110 objects based on what looks good from an imaging perspective, right? So let's be honest, a lot of things that look good through an eyepiece aren't really all that photogenic. And so we try to pick a range of objects in terms of size, in terms of type, so nebula and galaxies, a few star clusters. We wanted to offer something, for the Northern Hemisphere imagers, Southern Hemisphere. We really tried to cover everything. Yes, dark nebula indeed. Yes, we've got it all in there. And the idea here is, these are 110, we'll give you a broad array of things to image. And we spent a lot of time gathering data for all 110 objects. And you can see in the back, one of the unique things that we put from the beginning, Max and I decided we would provide all the details for each image in the book. So what filters did we use? What camera, what telescope, how long were the exposures, what was used to process it, where was the camera pointed, all of that. So complete details for every single image are included, and that's what you see on the right-hand side here. To give readers the lay of the land, we wanted to provide where where these objects sit in the sky. We wanted an all sky image. Actually, to be honest, it started out as just taking an image of a mosaic image of the Milky Way, like a lot of people do. And then, of course, like a lot of astrophotography projects, got completely out of hand, and we decided to cover the whole sky. So here's the image, and you can see the numbers on here are the locations of all the objects in the book, the 110 objects. Today, we're going to focus on this image, and this is what it looks like. So here's the full version in front of you. So this is RGB data plus H alpha data for the whole night sky. This is the whole visible universe. This is everything. And there's a lot of interesting things on here. You can, we'll dive into it in a little bit of detail later, but I hope the experienced astrophotographers are looking at this and immediately seeing, oh, wow, look at that. Okay, right in the center, there's M31. Oh, here's Orion, right? Here's the Magellanic Clouds in the Southern Hemisphere. Wait, what is this thing here? We'll talk about that, right? There's a lot in this image, but this is all your options, so to speak, but it gives you a sense of the scale of the night sky. And we're going to focus today on how do we take this picture, because this picture is 1 billion pixels. So we're going to break this into 3 parts. Planning, you don't just go out and take a picture of the whole sky right off the bat. Acquisition, so Max is going to cover acquisition, and then I'll come back and cover processing. All right, so let's go into planning. The planning stage started, and I had done some work for my prior book. Actually, we're going to do a poll question. I forgot before I jump right in. We want to keep this interactive. We've got a poll question for everybody. Okay, so what is the most panels that you've ever combined into a mosaic image? And if you haven't done a mosaic, we've got answer E up there. So Christian's got the poll ready to go. Call me if you are answering 100 plus. We should talk. We can talk shop. 20 to 100, that's still super expert level. I'm working on a 20 panel mosaic myself. But I think most people are probably going to fall in that 2 to 4 range. I think mosaics are pretty difficult. So let's see where they come in, Christian.
Yeah, we've launched it. Yeah.
Charlie, just to give people a few more seconds to fill in their answers, it's worth just mentioning for some of the audience who are maybe not so experienced with astrophotography that you can't just go out into the night and take a picture of the whole night sky.
Yes.
Because obviously, if you're in the northern hemisphere, you can't see the part of the universe that's only visible from the south. And that's true for the whole year round. We never, ever get to see the large and small Magellanic Clouds. But also, if you're taking a photograph in late August, there's a whole bunch of targets which are essentially now behind the sun. And so you have to do this project over a whole year in both hemispheres in order to photograph the whole of the night sky. So what this photograph that Charlie's going to tell you more about is what it would be like if you were an astronaut floating in space a long way away from the Earth and the sun and just able to look all the way around 360 degrees in each direction.
All right. Yes, exactly. Yeah. So, and hopefully some future projects will make that really come to life even more, Max. Okay. So haven't tried a mosaic yet, 68%. Okay. 2 to 4, 15. Very impressive people at 5 to 10, 14%. And someone out there needs to call me because they put 100 plus. All right. Awesome. Awesome. Okay. So we've got a couple more polling questions coming up later, but thank you. 32 panels of the Vela supernova remnant. Yes, that is fantastic, Peter. That does indeed take 32 panels. It is huge. Okay. So as Max pointed out, yes, you have to figure out, I had to create a plan to say, where do we point the camera, right? That's step one, is to say, where in right ascension and declination do we need to point the camera so that we get overlap such that we cover the whole sky, right? But to Max's point, the second thing is, when do we shoot those images and where from? So we had to set up, well, as you'll see, we had to set up a few sites around the world to do this, and also plan it so that we're pointing the camera in the sky at the best time of year for that particular area of sky. You may have heard spring referred to as galaxy season. So spring is galaxy season because that's when in the Earth's orbit, when you look away from the sun, right? So when you're looking away from the sun, that's like, midnight, it's the night sky. And that's when the Earth is in the part of its orbit where looking away from the sun points looking away from our galaxy, right? In the summer, you're looking into the center of our galaxy. In the spring, you're looking outside of our galaxy, and that's when you see the most galaxies in the sky, right? We call that galaxy season, and that's why. And so thinking about where we had to point, so we did all the math to plan this out. And again, I had worked on a prior project that was perfect for this. It allowed us to create a planner and say, which telescope should be pointing where on which days in order to do this. This is what the whole thing looked like. So when we put it up, this is 153 panels. That's what it turned out to be, to ensure adequate overlap using the lens and camera we were using, which Max is going to tell you about. It was 153 panels to cover the whole sky. This had to be spread over multiple locations. And then we realized after I calculated it for a couple of them that we forgot to align the turn, how the camera was positioned on the telescope. So they were turned at different angles in different locations. And we had to go back and make sure that everything was still going to be okay for that. We were good to go. And with that, then it was time to acquire the data. So Max, I'm going to hand it over to you to talk about how we did that.
Thanks very much indeed. Yeah, well, the answer is, yeah.
Reminder, we have another poll question coming up, Max.
Okay, shall I just give a little bit of an introduction to the system, because it'll put the poll question in context, I think.
Sounds good, yes.
We used, in order to have a manageable number of panels, just 153 just, we used this system here. We used identical setup in the Northern Hemisphere, and I'll explain the locations in a moment, and in the South. And at the front of the image there, I think you probably can't see my cursor moving, but the lens with the heating strap around it, the dew strap, that's a Samyang Rokinon 35mm lens, and it's a manual focus lens, and it's a surprisingly high quality lens, given that it costs only $400 or $500. Certainly compared to a refractor telescope, it's an incredible bargain. But it's beautifully sharp all the way to the corners, and it has a manual iris. Natively, it's very fast. I think I'm right in saying 1.4.
1.4. Yeah.
But we actually stopped it down a couple of stops, I think to f2, to take the pictures, because it helps address the absolute corners to try and get the most pinpoint stars. Then behind it, you can see our early attempt at focusing, which is an Atlas, a beautiful FLI Atlas focuser that moves the lens through just 9mm and has 105,000 steps in it. But in fact, we ended up finding a problem with that, because these lenses have internal optical elements. And so you can't focus the lens perfectly that way. Instead, you actually have to build a geared wheel to simulate your hand turning the lens. And we automated that. Then behind the Atlas focuser, you can see a slightly thinner, large circular black filter wheel. And we had monochrome cameras, so we were shooting in black and white, but with 7 different filters. The standard luminance, red, green, blue, and then the narrowband filters hydrogen, H2, O3, oxygen 3, and S2 sulfur. And all of the color pictures that we produced, therefore, were composite color pictures. And I know, Christian, you've run some superb courses to explain and seminars to explain how you combine those images together. But the red object at the back, that's our camera. And we used a Chinese CMOS camera, ZWO 1600, which has a resolution of about 4,000 by 3,000 pixels, an absolute workhorse. So very reliable, worked superbly right the way through. And then that whole package is sitting on an unusual mount. We used quite a new kind of mount made by a Korean company called Rainbow Astro. And these actually use the kind of motors that are used by NASA in the wheels of the rovers that they send to Mars. So they're pretty reliable and very strong. And I really like the Rainbow Astro mounts. They're very small, very compact, very accurate. And as you can see, the whole thing is quite compact for transport and setting up. And then an external computer to control it and so on, which I won't get into in detail. Now, that telescope you can just about see in soft focus behind is in my garden here in Holy Island, and that's Holy Island Castle. But if we go, I think, Charlie, to the next picture, we'll come back and do the poll shortly. There you can see the location a little bit better. Before we go on and explain where the other two mosaic cameras were located, let's go back and do that poll. And Christian, do you want to handle that poll?
Yes, I launched it. Okay. So once again, the question is on a tracking mount. So just beware, we're not talking about nightscape photography, right? We're talking about on a tracking mount, just what Max was showing.
So the question is, what's the shortest focal length lens that you've used? Because we had to use a 35mm in order to get only 153 panels for the whole night sky. And that's very wide in astrophotography terms. So is the shortest lens you've used 300mm or greater? That's the first choice. Is it between 200 and 300? Is it between 100 and 200? And the very popular 135mm lens, which those of you who use iTelescope will know is the lens on T70 and T80. That would be in that range. Then 50 to 100, less than 50, which is what we were using, or none of the above.
Fair number of people using shorter lenses than we thought, Max.
Yeah, that's very interesting. Yeah.
Yeah.
And just to be clear, this is on a mount, a tracking mount, not on a tripod, but
yeah. I suspect a lot of people have Polaris or Sky Adventures or some of those, because even 5 years ago you didn't do that as much, but now they have really nice small tracking mounts. That's great to see.
Great. So getting back then to where the systems were located in the southern hemisphere. We were a relatively early client, I think, at Deep Sky Chile. And this is Deep Sky Chile in the Andes. It's about 300 kilometers, I think I'm right in saying, from Santiago. The nearest big town is Ovalle, about an hour and a half away. And it is absolutely in the middle of nowhere. And it was built and created by this man here, who you can see holding up a beer after we finally got the system working. This is Frank Jobard, one of the co-founders of Deep Sky Chile. And if any of you are thinking of hosting your telescope in the Southern Hemisphere, I can really highly recommend Deep Sky Chile. And I'll be very happy to correspond with you if we're going to give our email addresses at the end. But just such a friendly bunch of people, really competent. And the observatory is absolutely incredible. It's in the middle of nowhere. At the bottom, you can see the very robust four-wheel pickup you need to get there. And in the background, behind the truck, you can see a range of mountains. And Frank's nearest neighbor at Deep Sky Chile is on the ridge line of that distant set of mountains, somewhere there, that's right. And it's actually the Vera Rubin Observatory, which is being constructed at the moment by a consortium that includes America and Europe and Chile. And it's going to be an incredible facility, but they put it there because this is absolutely one of the best places in the world. Here in Northumberland, I'm very lucky to have maybe 2 or 3 nights a month when I can observe. And during the time that Charlie and I were taking our mosaic at Deep Sky Chile, we were getting consistently 25, 26 nights a month. Just fantastic. Exhausting because you never got any sleep because you have to be up running the telescope, but superb clear skies. Now, the only danger is the 30-minute drive to and from the observatory, especially from. And in here, you can see the deadly cactus spines, which the cactuses that grow beside the road cast off. I think they might have a seed in the middle, maybe someone knows, but these are 6-inch long, like steel spikes, and they will go through the tire of a pickup, no trouble. So it's not too bad going slowly up the road in the day on your way to the observatory, looking out for these things and avoiding them. But when you're coming back at 3 in the morning, having failed to polar align for the 10th time, and your telescope's not working and you're exhausted, it's pretty scary. But fortunately, I managed to avoid that. So that was the southern setup, and on the right, actually, you can see what the view is from beneath our telescope on a typical night. The Milky Way, I mean, those of you who've been to Siding Spring, it's the same there, but just amazing to see the Milky Way, the heart of the Milky Way, so bright, breathtakingly beautiful. And on the left, you've got a proper view here of our system that's set up at our second main location, which is EI, which is a Spanish clever contraction of between the stars and the home oaks. And it's an observatory hosting facility around about maybe 60 miles from Seville in the hills, an altitude, I think, of about 600 meters. And it is also a superb northern hemisphere location. If anyone's thinking of hosting, I really recommend. They're so talented and friendly, and they look after your telescope, and everyone has their own individual observatory there with your own roof that you can control. But in the picture on the left from our telescope in Spain, actually, no, this isn't, but it shows that white nylon ring that's taken the place of the Atlas focuser. And this is what we ended up using. And it's a geared wheel that grips the lens. And then there's a stepper motor, very powerful, accurate stepper motor that drives the lens round. And that's how you do the focusing. I mean, it sounds terribly crude, but it's made by an American company called Regal Systems, very well engineered, a very clever mount on the lens itself. And I think for the next slide, Charlie, we go to see the software where we control everything for a night's observation to take this mosaic. And you can see there on the left, the focus curve that's being built up as you turn the lens through focus and past. And the really difficult thing with using these kind of DSLR lenses, as those of you who've done it will know, is to automate focus, because I think we might show it in the next slide. The infinity position is actually really close to the end stop of the lens. You can only turn it half a degree more and you hit the hard stop. And if you have a powerful stepper motor driving your lens past the hard end stop, you're in for damage, catastrophic damage, thousands of miles away in Chile, which you definitely don't want. So what we had to do is to machine the back of the lenses in such a way that we moved the point of focus closer to where that yellow triangle is in the right-hand picture. And that way, we could instruct the motor to go past focus, take a picture, past focus, and then back through focus and build up this kind of curve. And this curve shows the focus position. That's the x-axis, the numbers from 4000 to 4150. And on the y-axis is the sharpness of the image as judged by the size of the stars. And we want to find that sweet spot right at the bottom of the curve where the stars are as small as possible. And in order to do that, that's why we had to use this modified lens. If we could go back one slide, please, Charlie, thanks. The software that we're using here is Nina, and we were really fortunate in this project. And the heart of it took place in 2020 during the year of global lockdown, global pandemic. So it was an unfortunate but effective coincidence for us that we could really concentrate on running everything. And Nina was just such a superb piece of software. Again, I really recommend it to anyone who's looking to automate a remote observatory. Really superb, and it's been getting better and better and has a wide open source community around it. The other great piece of software which I should mention is Telescopius. And I know there's a connection with iTelescope, but that's a website you can go to and you can pay a subscription or you can use it for free. And it's superb for framing targets, finding the angle with your particular position angle and camera and sensor and so on. Telescopius.net, I think, and highly recommended. But this was our kind of control room, mission control every night. We had one for Spain and one for Chile, and using the playbook that Charlie described that he created for making the all-sky mosaic. Each night we knew we had a number of panels to go for, and we typically would take 20 or 30 images of every panel with the different filters and get all the data together ready for processing. And that's really the next step in the story.
Right, and as everybody knows who's done any astrophotography, the acquisition, unlike daytime photography, you're less than halfway there, right? So once you have the data, you're not done yet. I would guess that I probably spend 2 to 4 hours on any image, and sometimes even longer than that on the processing stage. So let's go into the processing, because in particular, this processing has 2 steps, which is one, we have to just process the raw data, and I believe, Max, for the book, between the mosaic, the 150 panels of the mosaic and the other images, we had about, I believe you said 6 terabytes was the total, right?
Yeah, that's correct. And very irritatingly, we use Dropbox for moving all this data around the planet. And Dropbox has a limit of 5 terabytes for any kind of affordable subscription. You start going into corporate territory if you get more than 5. So round about 90% through the project, that became a real headache.
Yep. So we had a lot of data. Some mornings I would wake up and find a tremendous amount of information ready to go in Dropbox to get processed. And Max would process the raw data, and then I would pull it into the mosaic. But I want to just talk about the fact that this is not a normal mosaic. When you create a normal mosaic, you have boundaries, right? So you're going to say, I'm going to take a 2 by 2. I'm going to take 4 images, and they're going to overlay, and there are clear boundaries. The full sphere is boundaryless, and that created some challenges. So in addition to the fact that we had terabytes of data, the computers can only handle so much. The software typically has settings, even PixInsight has limits in the size of an image that it'll let you deal with. And then you have to start thinking about all these strange things like projection choices. So I had to learn a lot about the different projections. You're familiar with, everybody knows that the Mercator projection of map has enormous distortion toward the poles, such that, Africa looks way too small and Greenland looks way too large. Things like that. So we had to think a little bit about all of these things, and they're not the normal things you have to do for a mosaic. But one of the things we wanted to highlight was gradient. So the other thing that people have, if you've had experience processing mosaics, gradients are the big challenge, right? So you've got different images that might have slightly different light pollution, or the moon might have been in a different place in the sky, or just even the way you adjusted the background might be different. And you have not only different background levels, but the image might still have some gradient from one side to the other. And then you try to put them together And those seams are become very visible in your mosaic because of those differences in background levels. And so everybody knows if you worked with a mosaic, like that's the big bane of processing for them. And we just thought we'd show here like sometimes what happens. So Max calls these inadvertent art. As we were starting to put the pieces together and we'd start putting panels together and seeing what it looked like. We ended up with some fun little images. I really like the one on the left. I think that stands as art on its own, but definitely not what we wanted to create the final image.
I think, in fact, Charlie, that picture on the left came out of Astropixel processor without any manual intervention. I just fed Astropixel processor all our data, and it produced that. And I think it's an achievement, even though it wasn't what we wanted.
It did align them. Yeah, definitely. Yeah. So I'm not going to go into the huge details because I don't, expect everybody to want to pursue 153 panel mosaic. But just to give you a sense of the scope of the project, in this case, we weren't able to just put the images together. We had to build a scaffolding image underneath. So you can actually do this. This is a very nice thing to do in PixInsight if you're doing mosaics there. You can use a function or a process called catalog star generator, and it will create a synthetic chunk of the sky for you. And then you can take your mosaic images and register them to that. And then as your mosaic's built up and you let it correct for all the distortion, it very neatly arranges your mosaics rather than trying to arrange your mosaic pieces to each other, where the slight distortion maybe in the field of view can make it difficult, and it has to do a lot of bending and stretching to make them fit. And then you get weird little double stars and things like that. So we took that to an extreme. And I mentioned that we were exceeding the capacity of even PixInsight. Catalog star generator only would build 16,000 by 16,000 pixel images. So we had to do 2, right? And then paste them together in Photoshop. And if you've ever opened Photoshop, it has challenges with images this size as well. And so it took us a while to even build a foundation image of the whole sky. Then, after we had processed each of the individual panels and trimmed them and integrated, registered, all that, gotten everything done there, we had these individual panels. We couldn't just paste all 153 on there. We had to build them in chunks. It's just unreasonable for lots of reasons. It's too hard to diagnose problems if you're doing it all at once. So we did at least 5 to 10 panel chunks. I'm calling super panels. So these were like 5 to 10 images, and you'll see what they look like in a minute. But all the tools will function with images that size. Then you take those super panels, you map them back to that first image we created, that scaffolding image, and then you can start putting the pieces together. You have to do this for each channel as well. So repeat this for red, then for green, then for blue, then for H alpha, then for sulfur, then for oxygen, right? This whole thing has to be repeated. So it's quite an undertaking. This was about 9 months of processing, actually. This image I want to show you, this is an example of what I was talking about for something like a scaffolding image. So if you want to put in the chat, what is missing on this? This is available on NASA's website. But if you look at this is an image of the whole night sky in some sense. But anybody want to put in the chat what they think is missing from this image? Or what's special about it? Ah, yes, great. Great point, Richard. Yeah. So, great point. So, yes. So, you don't see galaxies on there. Yeah, you don't see M31. It should be right here in the middle, right? Because this is actually not technically an image. I thought I'd show this as a great example. This is a plot. This is, they took, I think, I can't remember if it was the Hipparcos or Tycho data, but they took one of the
Gaia, I think it was Gaia.
Gaia, maybe it was Gaia. Yeah, yeah, Gaia again. Yes. So they literally took the stellar spectra. They said, oh, this is a type B0 star, so it's going to be a little blue. This is an R star, it's going to be red. They plotted them on here, and you get this beautiful image, but it's missing all the nebulae, all the galaxies, things like that. So it's technically correct. It's all the stars, but I just wanted to give you a sense of like what you can do, because actually you can create something fairly similar to this in PixInsight using the data that PixInsight has, which actually I think you can download the Gaia data and do that. But this was essentially the kind of scaffolding image we created. It's a plot of all the stars. And here's an example. If you zoom in, experienced astronomers and astrophotographers will recognize this little cluster, as would anyone like me who owns a Subaru, which is the Japanese name for the Pleiades. So here's the Pleiades. So this is not an image. This is that catalog star generator scaffolding image, a tiny, tiny little detail, this giant image we created that we were going to register everything against. Okay, so what's the overall process? So we took about between an hour and 2 of data for each channel for every one of the 153 panels. We then integrated those, registered and integrated in Astropixel processor. Then we took them into, we removed the gradient, we cropped them, so we had clean edges, and then they moved from Astropixel processor, and then everything subsequently for the mosaic building will be done in PixInsight. We won't go into all the details of that, but you have to linear fit all the panels so they have the same background levels, basically. Then you can register them with this mosaic by coordinates process, and then use gradient merge mosaic to try to blend together the panels into seams. And then you end up with a super panel. And we had ended up with 28 of these super panels. All right, so I just mentioned a bunch of different processing tools. We've got our third and final poll of the day. We just thought it would be fun to hear which processing programs you use. It's likely you use more than one of these, so I think we allowed it so you can check multiple ones, but we'd love to hear this. And while we're waiting for the results to come in, I will say, like, over time, I've used most of these, and it is funny how it's so much has changed in astrophotography over the past decade. And Astropixel processor has become, despite the learning curve, it's still the dominant and kind of all-purpose tool. Sorry, PixInsight is the all-purpose tool, but I find myself now using Astropixel processor for like what we did here, which was the integration, registration type steps like that, just due to sheer ease of use. I will say that weighted batch pre-processing has made it a lot easier in PixInsight.
Yeah, Charlie, just very quickly, so this is multiple, you can have multiple answers. I just wanted to throw it in. Okay. Yep.
And I know a lot of people still use Photoshop. That's a great place to start. You can generate great images, frankly, with all of these tools. It's just a matter of which tool you become used to using. All right. Oh, wow, look at that. A lot of love for Astropixel processor. That's great. Mabula would be thrilled. And again, I think that speaks to the ease of use of that. PixInsight, though, Photoshop. Oh, great. Some star tools and nebulosity users still, Maxim VL, Deep Sky Stacker. Wonderful. Wonderful. It's great to see a lot of expertise spread all over. Okay. All right, so let's get into let's talk about what these mosaics start to look like. All right, so I mentioned that we're going to use this all sky projection. This is called an equirectangular projection. It's similar to, not quite a Mercator projection, but it's a projection you would have seen of world maps. And I just wanted to show what you have. So you take a rectangular picture. This is one panel. This is an example, though, of you take one panel, you can see it was actually taken at an angle, and then you reproject it. So PixInsight amazingly has tools like this that you can do that and reproject it into this new projection. And so you can see what that looks like, and you can see the distortions that it generates, so to speak. When you take about 6 or 8 of those individual images, those panels, and put them together, and I was talking about those super panels, so we had to get all these chunks. And so the goal here was, you see the super panel, was to make sure this looked seamless, right? So you don't want any of the seams to be showing, as little as possible. You're trying to avoid the seams. So this is a successful super panel. It worked to get this one panel looking good. And just to give you a sense of the scale of the image, right? Again, we'll use the Pleiades M45 as an example. And you can see if you zoom in, this gives you a sense of what it looks like. And now, unlike the scaffolding image I showed you before, this is an actual image, and you can see the reflection nebulosity, all that dust around the Pleiades. So there's a super panel. And I'll give you an example of a different one. And again, we talked about sort of what the reprojection looks like. This is an extreme example. This is when you get all the way up to the pole. So this is 4 images. And you can see, I think we've gotten all the seams removed here. Everything looks really good. but you can see this is just 4 images, and as you reach the pole, like this is how they get stretched, because right at the pole, 1 hour of right ascension as you move actually isn't moving very much in the sky, right? Like whereas you get down to the celestial equator, you're moving, you know, a lot across the sky, 15 degrees to be exact. And this, just as a memory, maybe just for me, but this was just a reminder, this was not like a totally automated process, right? So this was me mapping these out and planning out, okay, this is what makes sense as a potential super panel. These are the images I've got today. Let's take these 6, let's put them together. Let's take these 8 over here, let's put them together, and creating the panels and building this as we go. Also studiously avoiding the edges, because those were the most difficult part. Okay, so I've built a couple of the super panels. I go back to that NASA image just to see, are we on the right track? Is this going to match? So go into Photoshop, set transparency, slap one of our super panels down, and sure enough, the first super panel we did, PixInsight had perfectly reprojected the images and the stars lined up perfectly. And I was like, yes, okay, this is great. So now we've done this with 1 super panel. Let's do it 28 more times. So we won't go into this. This is you know, months of work in the evenings. But it was really exciting because you could see the sky kind of building up like a puzzle, right? It's building up. It's very exciting. And this was when we finally had all the 28 super panels consisting of all 153 images together. This is when they came together for the first time. And okay, we can see some seams. There's some gradients here. There's still some work to do, but it was fantastic to see the whole sky in one place.
And Charlie, also worth mentioning, it was a huge relief that we hadn't missed out some piece of the jigsaw puzzle. So maybe down the bottom left there was a missing triangle.
Yes, we actually were able to fill that. And that missing triangle was actually where I had trimmed the data and we were missing a little piece. And so I went back and it's like, ooh, I think we had like some subpar data. So technically that's like the lowest SNR part of our whole image. But overall, it all came together beautifully, exactly. Now, I did put 2 arrows here. Anybody want to put in the chat what they think is going on here? Why did I call out those 2 stars? And somebody got it earlier.
Yeah,
there
well
done. Exactly right, HM Tang. Yes. So I can't. It's either Jupiter. I think it's Jupiter and Saturn, or Jupiter and Mars. And that's exactly it. These are not. I had to take these out. And what's going on here is that it would have been kind of neat to leave them in, but I couldn't even quite leave them in because we took, for instance, H alpha one night, and then it might be 3 weeks later that we took red green, and then 2 days after that we managed to get the blue image. And so the slight movement of the planets was leaving tiny little trails in the image, and so I had to go back and trim out the planets. And you know, technically we kind of didn't want them in the image in the beginning, but that was one thing we didn't even think about from the beginning, but we discovered where the planets were pretty quickly and what their orbits what their orbital path was. So this image right here, this is my favorite. I like the main image, but this one I just enjoy a lot because I love narrowband photography. This is the just H alpha. So this is the whole night sky in H alpha. And let's just take a second. I want to point out a couple of things here that you might know. So yes, you can see M31's here, and M31's just bright in general, and even an H alpha filter is going to pick up some of just the broadband emissions. But you can see here, there's the California Nebula, right? Here's the Heart and Soul Nebula over here. Here's the IC 405 and 410 in Auriga, Orion, Barnard's Loop. That tiny little part right there, that's the Rosette Nebula. You've got, you know, the Seagull Nebula down below. There's a couple things that you wouldn't even notice if you had an image this scale. So what is this thing right here? So this is very rarely imaged. It's called a Fishhook Nebula. It's only cataloged by Beverly Lens. I think it's LBN 853. It spans like 15 degrees, just gigantic. It's an old bit of supernova remnant, super faint, but shows up beautifully in our image. I was so excited to see this. And then you might notice this monstrosity down here. This is actually, so this is an object we put in the book. So I forget what number it is, but this is GUM 35. This is the largest object that we put in the book. This whole cluster, this whole area of nebulosity down here. And you can see the Vela supernova remnant is actually part of this, but this covers an even broader area. You got the Magellanic Clouds down here. You know, the veil in Cygnus, right? So the whole Western veil, Eastern veil, that whole thing is just this tiny little area right here. So this is my favorite part of the whole thing. But then you take this and you overlay this to enhance the red channel of an RGB image.
Charlie, sorry to interrupt, but yes. It's worth mentioning that the image is far higher resolution than we can see in your slide here. I don't know whether it's possible for you to zoom in at all, particularly on the H alpha one, but yeah.
Let me zoom in here. I have to move my chat around a little bit, but yeah, we can zoom in. That's why actually the file for this presentation is 130 megabytes because I left them fairly high resolution, right? So here's the California Nebula. Here's Auriga. This is the Zeta Orionis image just over the top of Orion's head. There's the Rosette. See the seagull down here. But yeah, it's just so much fun to just play around, zoom in on bits of this. Let's see. Here's Cygnus, right? North America, Pelican. The veils down there. This is Sharpless, I believe 126 or 106. This is where you see the bat, Sharpless, I forget what number that is, but the bat with OU4, the super faint planetary nebula. This is like, you can just scan along the Milky Way, and this is like every great astrophoto you've ever seen. You can see where it is in the sky. So if I go back to the main view, so here it is with everything put together. And here you can now see some of the broadband objects stand out a little bit more, right? So here is, I showed you the Pleiades, right? But you can see how that blue reflection nebulosity there didn't show up at all in the H alpha, shows up brilliantly here. Here's Rho Ophiuchi, and you can see the Antares yellow reflection nebula there. You know, that whole area, very colorful. The Magellanic Clouds just show up beautifully there. So this is the whole thing. This is the whole shebang, the whole night sky, all put together finally. And then just to give you a sense of what you're looking at as a remote, because it's easy to get lost, right? What am I looking at? I have no point of reference, right? We can overlay the constellation lines and you can sort of see things. So now you can get a sense and you can see, right? So when you are looking at galaxy season in the spring, for instance, you are looking over here, right? Canis Venatici and Coma Berenices, Virgo, like this is when you're looking outside the Milky Way. And then as you move later in the year into summer, right? Now you're in the Northern Hemisphere, at least we look into Cygnus, and then you go across summer into fall, and you got Cassiopeia, and you fall into winter, you start to see Auriga. Like this is moving from right to left is actually like moving through the year, basically. All right, and that is one other thing that we did with that image in the book is we used it to divide the like chapters, basically. So we took the Northern Hemisphere, divided it into 4 parts, one for each season. Same for the Southern. We ended up with these 8, and we called them octants. And when they were able to take that H alpha image, reproject it, and again, sort of show where all the marquee objects are, right? So 28, you might recognize that's the Ring Nebula. You know, 15 and 16, right? So that's the North American Nebula and Pelican Nebula. But there's probably some targets you might not have thought of to exploring in here as well. But we just sort of show where they are, and it gives you, again, it gives you perspective on where these things are in the night sky. All right, so this is just a representative page of the book, and I just want to show you one other thing, and I do believe it's helpful to zoom in here. One of the things we did for each of the 110 objects in the book was, you know, a little bit of description about it. This is Wolf's Cave, discovered by Max Wolf. This is a complex of dark nebula, reflection nebula, and emission. And you get some description of it and stuff, but what we wanted to show with this chart is how many imaging hours can you expect from different latitudes to be able to see this object, right? So this is not sunset. This is time. The clock starts when the sun gets 15 degrees below the horizon, when it's fully dark. And then, okay, how long is this object above 30 degrees in the sky? I think we 25 degrees, the threshold we set. So when is it in reasonable position? This gives you a sense of when should I target this, right? So if you're thinking about targeting it, let's say in August, you might say, okay, well, if I'm at 40 degrees, which is purple on here, maybe I should wait until later in the winter because I'll be getting 10, 12 hours of imaging on this object every night when it's clear.
So, Charlie, the different colored lines essentially represent different latitudes, don't they? Yep. So there's no red line in this one because Wolf's Cave isn't visible from the Southern Hemisphere. But,
that's exactly right. So those of you in the Southern Hemisphere, you have all those wonderful objects. You've got the Tarantula Nebula and the Vela Supernova Remnant, but you don't have Max's Wolf's Cave here, right? This is this shows that, yeah, the red is not even plotted because if you're at 30 degrees south, it's not visible to you at all. And we chose these. We didn't want the chart to become too convoluted with 20 different lines on it. This covers all the major population centers, and you just sort of pick the one that's closest to you, right? This is to give you a sense of what month you should be imaging, not precisely how many hours you're going to get each night, although they are precise for that exact latitude. But you just pick the one that's closest to you, and this should cover most of the major population centers of the world.
Charlie, one other thing, if you just scroll down to see the image on the right,
yeah,
this is a good opportunity to acknowledge someone else who was really important to the project, particularly early on. And that's someone many of you will know, Mladen Dujek at iTelescope, quality manager there. And Mladen was enormously supportive and helpful to us in the early stages of the project. And very, very sensibly, he decided he didn't want to spend every waking moment of his life processing images. So
smart man.
Yeah, but the three of us put this image, which I took here in Holy Island, actually, from my observatory here. We submitted this to APOD, NASA, and it was awarded an APOD back in September of 2020, I think. Anyway.
Yep, and I think it speaks a lot to the project, Max, that this image got the APOD. But actually, I think later on that's not centering anymore, but when we came back later and shot the same object again, you can see it here, I think we got an even better image of it the second time.
Yeah, well, and something else that we should just mention before we get to the commercial, which I see coming up, is that many of these images were taken using the iTelescope network, particularly the longer focal length images in the Southern Hemisphere. I don't know the exact number, but certainly 30, maybe 40 images were shot on iTelescope. And for those of you who are using the iTelescope network, we hope that this will be a useful reference work to see the kind of magnification and quality of images you can get from the different telescopes. Of course, the telescopes come and go a bit, so some of the ones we use may not be exactly the same, but I think it'll give you a pretty good idea of what you get, and also the difference between CMOS and CCD, which of course is a transition we're living through at the moment, quite interesting.
Yep, and you can see exactly which iTelescope by number in the back of the book in the appendix that we used, and how many exposures, what duration, all of that for you. So that's it. That's the journey. I'm so happy you guys came along with us on this journey. This was our pandemic project, so to speak. I'm glad Max was able to get the cameras and telescopes out there before the pandemic started. But the final result was, or at least the first result of this project was the book. We'd love to share that with you. Its list price on Amazon is $75. It's 55 pounds. For viewers of this, we're going to offer a discount on that through the end of September. 65 in the US, 45 pounds in the UK, and all including shipping, 60 euros shipped in EU. And then the rest of the world, shipping can be highly variable for us. As you may be aware, very few people get rich publishing a book, so the margins are not 100% on this. So we will have to do $55 US plus shipping at cost for the rest of the world. Do our best to offer it to you at the best price we can.
And what I'd suggest for practicalities is that our email addresses are there, and any American or people from whom shipping from America would be the logical thing, like Mexico and Canada and so on, please contact Charlie, and there's Charlie's address. And anyone anywhere else, please contact me, and we could sort out payment by PayPal or probably credit card, or we'll take cash if you want to come to Holy Island too.
Yeah, and just to add one thing, it says offer for active iTelescope subscribers. So please also add your current username, because we will check that, right, for this offer.
Yep. Thank you, Matt. Thank you.